Afternoon, everyone. Look, really great to see such a turnout for the interest for the railways in Ireland, and in particular the Permanent Way. So, thank you for coming. Yeah, look, our presentation today is going to be on rail milling. I get the easy bit. I get to do the introduction and the conclusion. Bob gets to do the hard technical bit in the middle. Okay. So, look, TransLink, like all rail companies, our funding is a mix of revenue and capital. Over the years, again, like most railway companies, the investment in public transport, and in particular the railways, couldn't keep pace with the level required. So we've seen the average age of our assets increase. This has meant that the maintainer, me, has needed to find mechanisms to cope and sweat the asset beyond its designed life. Over the years, the defects we found in our network have changed. We had predominantly jointed track many years ago, so the real defects that we found were rail end batter and star cracks around the bolt hole. As we upgraded our network to CWR, our defects changed with time as well. We found then that we were having more rail contact fatigue type defects like squats and other running band defects as well. This slide here shows how we categorize our defects into three distinct categories. So you have phase one, which is the early life of the rail, essentially brand new rail. Looks pretty good, no defects found. Half-life, we're starting to see then some non-actional defects, some minor cracking along the head of the rail, and then into beyond the half-life, into phase three, where we're starting to see an increase in actional defects and unfortunately severe RCF appearing as well in certain circumstances. So we developed a rail health strategy then to help us cope with this. We looked at our routine track maintenance, and we also looked at how we ultrasonically test the rails. In TransLink, the way we test, everything is done in the one night. We test, we verify, and we remove the defects all within the same shift. It's labour intensive, it can be hard to do, but it means then we reopen the track in the next morning and we have no TSRs, and any actionable defects that we found have been removed. As part of our rail health strategy as well, we look to upgrade our key components. So this slide shows us an old, tired-looking, life-expired IRJ, battered ends, upgraded to the new factory-assembled glued joint. We also looked at SMW wells. You heard that mentioned in one of the presentations earlier. So SMW wells, look, they have the potential to lead to rail breaks. So we put a program in for our rail health strategy to remove these SMW wells over a period of time, and we're currently working through that. So this strategy needed something, I suppose, then to cap it off, to once we got the rails, the defects removed, we had upgraded the key components, and we removed the likes of the SMW wells. We needed something then to come in and take any of the micro cracks that were left in the head of the rail. So fortunately, there was a rail miller on the island of Ireland, and we've been utilising that over a number of shifts over the last number of years to bring our rails into good condition. I'll put this slide up. It's always one that I worry at times about putting up, but look, I've decided to do it anyway. Strategies tend to have outcomes, and you tend to look at a strategy and how you measure your outcomes. They have to have a purpose as well. So the Hatfield crash in October 2000 reminds us of the importance of having a proactive strategy to manage our rail defects. Safety has to be the number one priority. I'll hand over to Bob now, and Bob will go into a wee bit more detail even with Hatfield, and then lead on to milling. Thanks, Bob.
Good afternoon. Hatfield was an eye-opener for me. As young in my career, only been on 12 years, I think I'd been on the railway, and I got a call on an October night to go to the Hatfield site. And our task was to actually collate rails for the police to take away. And nothing I'd seen derailments before, I'd seen goods vehicles come off, engineering vehicles come off, but I'd never seen anything like this, nothing at all. And yeah, a real eye-opener that I hope a lot of engineers and people within the rail industry never see now. That's the prime. This is what it looks like when you have an asset with a single point failure fail. The guys and girls that used to look after this sort of section of track, they thought they were doing everything right. They had the worst defects clamped, and for unknown reasons, one of those cracks, out of hundreds of thousands of them, over 3/4 of a mile of track, one broke under the train. That set off a system of brakes that went through, and there was over 300 brakes in that rail in the end. And it led to 4 fatalities and numerous injured. The outcome of the whole scenario was Railtrack, who was the asset owner or governor, they lost their position, the company got shut down, the Network Rail. Guys that I knew faced prosecution, and it was a bad time. And I asked people, you know, if you were running that piece of railway, how would you have looked after it? Would you have clamped it? What would you have clamped? Yeah, would you have put a speed on it? That was on the down fast main, which was a central road. Putting a speed on it, it may have still broken, come off, hit something coming the other way. Would it really have been mitigation? And it leads you saying that really the mitigation for that site is don't let your rail get that bad. It's a single point failure asset. There is no other safety system. So this is where rail milling comes into it. So I'll carry on with my presentation. Linmag, international company, we carry out rail milling throughout Europe, UK, Ireland, Australia, various different machines, but here's our Irish machine. It came in one machine at a time. This is Erin. We were doing about 100 shifts a year, and that's gradually picked up and gone up and up. And with TransLink now, we're at about 250 shifts a year on Ireland, putting their rails right. Some of the more prestigious places we've worked as well, Sydney Harbour Bridge, because our processing is no risk of fire or hot debris. We could go and process Sydney Harbour Bridge and not any fear of dropping sparks and that on the holiday makers underneath taking the pictures. Step into the history of milling. Milling's not a new process. It's been around since the 19th century. It's non-abrasive, as I say, it doesn't cause any sparks. It takes chips out of a workpiece at very precise levels, but no one had ever done it on a piece of rail before. Lynn Singer, who's at the OEM company, part of us, they worked together with Deutsche Bahn originally when they learnt of the problems of micro-cacking in rails, and rail was getting scrapped out prematurely, was could we do something with milling and remove deeper defects? So they took a couple of their milling units, they inverted them, developed them, and that was it. The first rail milling truck was born, or machine was born, where instead of the workpiece normally moving under the miller worked over the workpiece. It allowed rail management to have a fresh load of strategies, because now all of a sudden you went from, well, I manage my defects, I measure my defects, I might grind my defects, and at a certain depth I've got no other opportunity but to renew my rail. And most of us were renewing rail around Europe way before its life expired. We're talking rails that are 1-2 millimetres worn in that way. It also gave us the opportunity to recycle what we removed from the rail. You know, this is something we'd never seen before as well. Grinding, we don't pick up the material. But so it added to our green footprint that we could recycle this high-grade material as part of the process. If we look at defects that we look to manage, and we look at how a growth rate is, a growth rate of a defect starts with small embryonic cracks on the surface of the rail where the metal gets life expired and they start in a slow horizontal plane. And as the tonnage builds up, and more tonnage runs over it, so they gradually creep along horizontally but gradually going down. And then as they drop through this rail surface stress, you'll see at the right-hand side of that centre diagram, you'll see the cracks start to turn down. That's normally about somewhere between 2 and 3 millimetres. Once that crack turns down, exponentially, the internal stresses of the rail cause the crack to go faster and faster. So you've got to have something that we can achieve to get that defect when it's turned down as well. This is what we found. Grinding was all right. We were treating the very surface cracks, but we hadn't got enough grinders in the UK. We had 8 machines, but we couldn't keep on top of all the cracks. Still, they got to the point where they turned down. We went into a cyclic mode, really, within the UK. So you're cyclically grinding, you're chasing defects, and eventually we get to the point where we have to go into a corrective strategy. And the corrective strategy we only had before rail milling was rail renewal. All of a sudden now we can go down and we can monitor everything with eddy current and we can take deeper defects out. This comes back round to Hatfield again. As part of the approvals for this technology, 14 years after the Hatfield derailment, I took rails out of the Hatfield site that were life expired, had massive defects in them, we'd had to remove them and re-rail. I took those rails to a static milling plant in Switzerland, and there was 2 things we needed to do. One was to prove that our detection systems, our measurement systems, were giving us the right answers, and 2, could rail milling help us? We milled those Hatfield rails after 10 years, and we totally removed all defects, restored the profile, and that was with 6 millimetres of material removed. Now people think, oh, that's a lot of material to remove from my rail. In the previous 10 years, it only worn 3 millimetres, and that was with the grinding we were doing as well. And I still had another 3 till I hit my minimum rail depth. So fundamentally, we worked out that we could mill a rail, get those defects out at the worst possible time probably. You know, they weren't the optimum time to treat the rail, and still extend our rail life by 10 years. And I think I still monitor Network Rail's success with their machine. And at the moment, they've done something in the region of 500 shifts with their machine. And the cost that they've saved is about £500 million in compared to their re-railing cost. How does milling work? Milling is a climb milling process, whereas you'll see at the top of it, it takes a wider, broader cut, and as we come down towards the workpiece, it shallows off. And the reason that we used this climb process was we didn't want to introduce any heat into the workpiece. Anyone that knows about rail steels, if you can minimise the heat into a rail piece and not affect its structure, it's all good for the rail. So this climb milling was invented for the rail. This shows you the difference between milling and grinding as far as heat is concerned. With our climb milling, we can keep below the 730 degrees. As I said, all the heat is in the chip and the tool. We see with multiple pass grinding, which was the only option we had before, every pass we did, the heat was going up and up and up because it retains residual heat. And this is what you end up with. The martensitic layer in the middle, or the trigger point for martensite, we see the rail grinding going up above it, and we see the milling sitting below it. This is backed up by other studies done by various other universities. And on the left, you'll see an exploded view of a rail. The crystalline structure is still pearlite, whereas on the right-hand side, you'll see it's starting to go martensitic and austenitic. And what that means is you're introducing not only a non-conformal flat profile to the rail, it's also with brittle parts in it as well. So we're quite proud that we can mill and polish without affecting any of the metallurgy. Another byproduct that we didn't know about until we'd done some studies was our surface finish and roughness. Because of the finishing techniques we applied, and they were developed and designed by Linsinger, nothing like it had been done by anybody else, our surface roughness was so much better and in a longitudinal plane. So we found where we've done work for people like Docklands, we do work on Crossrail, where noise and vibration is critical. They get complaints left, right and centre. Crossrail, the Elizabeth line is censored, and we meet all their targets. We've quietened rail down by 50% from a new rail. Material removal. One of the things I always get told is, well, I'm really worried if I mill my rail, I'll have no rail left. Well, if you don't mill your rail, you're not going to have a rail left anyway, you'll end up chopping it. So but we do actually, if you look at the sort of Y0 in the centre of a railhead, when we're doing conventional, not too bad at profile rail, yeah, if we say we're taking 1 millimetre off, it's 1 millimetre deep. If we switch to something that's perhaps got a bit of plastic flow either side, we can say that we're taking 2-3 millimetres off, but when we actually look at Y0, it's sort of 0.5 to restore that profile. So not always, as we say, using your rail up needlessly. Another benefit of the milling process, and this was learnt in Germany actually, was by design some curbs end up with a tight gauge. So you can do gauge widening with milling. It's only a matter of setting the Y0 and we can put the shape of the rail slightly across, widen the gauge. Before it used to be hours of work, either repadding, nyloning, screwing, whichever. So the Deutsche Bahn really liked that one. And here's what we're talking about RCF removal. Our machines, dependent on the machine, you can take from 0.2 millimetres off in one working pass up to 6 millimetres. The big network rail machines, they'll do 6 millimetres at a kilometre an hour. And last but not least, we were talking earlier, someone was talking about replacing components in S&C. One of the biggest benefits I saw as a route engineer was when I started milling S&C. Because historically they're made up of different components. We replace a switch rail, we replace a crossing, we replace this. And then we expect everything to run through flat and true. But if you can put a milling machine through it, we can now flatten those different components out and you'll get a better ride through it. Latest technology on the machines that are working in Ireland is that we can work to within 15 millimetres of the switch tip. We work right up to the joggle on the nose, and as soon as we're across the transfer port, we can drop back on the back of the nose again. So really good treatment now in S&C. Just to sort of recap really, so we're carbon friendly with the biofuels, the Irish vehicles that we use in Ireland, we're actually told we're negative carbon. We actually award you points for using us. So that's good. Don't know what it'd be like with the rest of our machines. We've got some machines that are hydrogen, we've got some machines that are now electric, and we've got the conventional diesels that can all run on biofuels. We can treat light rail, heavy rail, yeah, and from a rail engineer's point of view, the one thing I like about it as well, what I prescribe as that that rail contour, whether I want 0.2 off the corner or whatever, I get it with that milling shape. We make the shape for you. Thank you very much.
Sorry. Look, I'll run through the benefits very, very quickly because I know we're very tight for time. On the left-hand side of this picture, you can see the rail that has liquid dye penetrant testant on the head of it, and you can see the micro cracking then that's on the running band. The middle picture shows us after we've removed 1 mil of material following one pass of the miller, you can still see a little bit of micro cracking. The clearest picture then is on the right-hand side where you have the 2 mil removed. Really, really clearly, that micro crack and any of those surface defects that were present in the head of the rail have been removed. Look, we're going to hear a lot about sustainability, and sustainability for us as engineers should be, it's really up there in the things that we're thinking about. This is potentially rail that could have been scrapped. There's defects there. You could have looked at it and went, you know what, the best thing for me to do is remove that and get rid of it. With the miller, we're able to come in and take off 2 mil of material. Okay, you're losing that 2 mil of head, but you're still keeping the rail there. So that is a sustainable product. You can see then the 2 graphs here is the eddy current test and showed graphically. So pre-milling, you'll see a lot of those spikes. Those spikes are all cracks in the head of the rail. You can see quite a lot, quite dense, sort of cracks in between the 1 and 2 mil increment. Post-milling then, you can see very, very clearly how that's been wiped out. So those are potential defects, those are potential cracks and potential future failures that have been taken out by milling. The next slide then shows us, again, you can see very, very clearly, and these photographs were taken at the exact same point. The profile on the head of the rail, you can see how it has changed and worn with time. The defects on the head of the rail, which is pitting and just bits of dirt and things like that that have been ran into the head of the rail by the wheel. Post-milling, then you can see that how that rail head idealized profile has been restored and those pitting defects have all been removed. I'll end with, look, a couple of statistics. We introduced our rail health strategy in 2020. Prior to that, TransLink were getting in around 1 or 2 rail breaks per year. Since we've introduced the rail health strategy, so removing the defects, removing the SMWLs, upgrading our components, topped off by milling, we've seen 0 rail breaks in 21, 22 and 23. One of the big wins for me personally as well was our actionable defects per track mile. If I look back to 2019, 2020, we were getting quite a high number of actionable defects and our defect ratio was sitting at 1.03. So within those 4 years, having went through that with the rail health strategy, we've managed to bring that down to 0.55. So look folks, sorry for overrunning a little, but that's the end of the presentation. Thanks very much for listening. Thank you.